Good afternoon, everyone here and online. So my name is David John Gagne. I'm the head of the Machine Integration and Learning for Earth Systems Group, or MILES, and CISL. I'm pleased to welcome our guest speaker today to the CISL seminar series, is Dr. Duncan Watson-Parris. He's an atmospheric physicist working at the interface of climate research and machine learning. The Climate Analytics Lab, or CAL, he's at University of California, San Diego /Scripps Halıcıoğlu Data Science Institute. He focuses on understanding the interactions between aerosols and clouds and the representation within global climate models. These interactions are numerous and complex, involving nonlinearities and feedbacks, which make modeling average responses to any perturbation in aerosol extremely challenging. Cal is leading the development of a variety of machine learning tools and techniques that alleviate these difficulties and ultimately combine with a variety of observational data sets, including satellite and aircraft measurements, to constrain and improve these models. Duncan is also keen to foster the application of machine learning to climate science questions more broadly, and convenes the ML for Climate Science EHU session and co-convenes AI and Climate Science Discovery Series as part of the United Nations AI for Good program. So without further ado, we're going to hand it over to Duncan.
Awesome. Thank you very much, DJ, and thanks for the invitation. It's great to be here. I won't actually talk very much about the satellite side of things and the observational side. I wanted to focus here more on the machine learning for modeling aspect, and I will introduce all those complicated sounding details of the climate system that I'm focusing on. DJ gave a very good effort at pronouncing the Halıcıoğlu Data Science Institute. It's a bit of you have to just ignore how it's written and just go with it. But yeah, so in this talk, I want to talk about how machine learning might accelerate climate science and focus, as I say, on Earth system emulation. I'll give a brief introduction as to what I mean by Earth system and what aspects of the Earth system I focus on, and indeed actually also what I mean by machine learning. And then I'll give three examples, case studies, if you like, of how we've used this in the lab. So the first is for improved UQ, uncertainty quantification and calibration. Also for exploring future climates, and also modeling spatiotemporal noise. And we'll come on to what I mean by that a little bit later on. And I'll give a brief outlook and describe some future work if I have time at the end. So machine learning, maybe I'm in a safe space here. People are kind of okay with the concept of machine learning and how we might use it, but it can divide the room. So I just want to briefly lay out what I mean by machine learning and how I think it can be useful. So driven by developments in both the hardware and indeed the software, but primarily the data as well, collected by leading companies in industry, Google, NVIDIA, DeepMind, part of Google, but also recently OpenAI. I have to keep updating this slide every few months to add new examples, but driven by these developments in industry, there is a kind of proliferation, if you like, of projects and collaborations across the sciences. These are just some examples off the top of my head in the climate sciences, where people are looking to explore and understand how we might use these and harness these new tools to improve the science that we do. I think from my point of view, much of these tools are going to accelerate and improve the way we do things already. I don't think necessarily we're looking at a complete transformation of the way we do things. I don't think we're going to throw away a lot of the physical models that we've been relying on for decades. But that's not to say there aren't opportunities. And so I'm trying to kind of thread the needle between people who are maybe skeptical of some of the hype that are coming from industry, but acknowledge the fact that there are novelties and utility in these tools that are being developed. I also want to point out that NVIDIA are a little bit guilty of this, but other hype machines as well, sometimes conflate the idea of machine learning for weather and climate. And many of you in this room will appreciate the distinction, but I just want to make clear that these are two very different things, right? So in the weather setting, so I'm focused here on the UK, where I spent a lot of my life. The weather task is really just integrating, getting the best representation of the initial conditions of this beautiful chaotic system and integrating them forward in time as best we can. And we've got pretty good at doing that, and NVIDIA and others are leading the way in thinking about how we might use machine learning to accelerate that. But I'm thinking about this from a climate setting, and in a climate setting, we have as we look over larger spatial scales and we start to average over longer temporal scales. So I'm now starting to average this cloud field over days and weeks and shortly seasons. You can see that this becomes actually a much more tractable problem. The average response of clouds to the changing insolation through the seasons is much more predictable than any individual weather state. And so all of the kind of climate model emulation that I'm going to describe in this talk is of this second type. It's looking to understand the statistical response to a change in boundary conditions. So all of the emulation I'm going to describe is of that kind of boundary condition problem, as opposed to the NWP stuff that NVIDIA and people have been working on. Okay. The particular aspect of the climate system that I'm focusing on, and the science, if you like, that I'm interested in, is the role of aerosol in the climate system. So these microscopic particles come from a number of natural and anthropogenic sources. But it's useful to picture some pre-industrial state to understand the role of aerosol in the climate system. So if we go back 150, 200 years or more, the primary sources of aerosol in the climate system would have been, does this work? There we go. Dust particles, sea salt particles, maybe some organic aerosol emitted from biogenic sources. And the two primary ways which this aerosol interact with the climate system are by directly reflecting some of the incoming solar radiation back to space. So these particles scatter shortwave radiation. Some of that shortwave radiation gets scattered back to space. The second primary physical role that these particles have in the climate system is that they provide the nuclei on which cloud droplets form. So water vapor rises, cools, it wants to condense, and it needs a seed in our atmosphere to condense onto, and aerosol particles provide that seed. Clouds obviously play a crucial role in the climate system. They cover 2/3 of the Earth's surface. They reflect 1/3 of all incoming solar radiation back to space, and they provide all of the fresh water for all of life on the planet. If we flash forward to the present day, we've introduced a soup of other particles from burning fossil fuels, other industrial activities, desertification, and so on. And these interact in complex, nonlinear ways with the existing aerosol in the system that make it very hard to disentangle from observations of the present day, which is what we have available, what exactly the effect of these aerosol are. But we can characterize those effects again in kind of broad strokes. Primarily, if you add more aerosol, you increase the optical depth, you induce more scattering, and you reflect a little bit more sunlight back to space than we did before. This is a so-called direct radiative effect of aerosol. The eagle-eyed among you might have noticed that our cloud got a little bit brighter as well. If we go to the present day, if we introduce more aerosol, we have more condensation nuclei available. So for a given amount of cloud water, you end up with more smaller cloud droplets. And those, if you work through the geometry, mean you end up with a higher surface area in your cloud and a brighter cloud. So this Toomey effect, it's so-called, induces another cooling. It reflects a little bit more sunlight back to space. And in fact, probably best estimates about twice this direct effect. It does something else as well. If we have smaller cloud droplets, you might inhibit or at least delay the onset of precipitation. And that might in turn make the cloud live longer, a so-called lifetime effect. And if you have clouds that live longer, then the areal area of the clouds is larger, and that induces a further cloud brightening effect. So another cooling due to this aerosol. And as we go down this chain of processes, the magnitudes of the cooling, of this forcing, we refer to it as, gets larger, but so do the uncertainties. And so a lot of those uncertainties stem from the fact that, as I say, we can't observe the pre-industrial. We rely on models to model these effects and discern the difference between the present day and pre-industrial. You've all seen this slide dozens of times in the past, but just to kind of refresh your memory, we discretize the Earth into these little chunks in order to be able to integrate the large-scale atmospheric motion. And any of the processes within these 10, 50-kilometer grid box, even 1-kilometer grid box, if we ever get to 1-kilometer grid boxes, all these aerosol processes and cloud processes will have to be parameterized. We have to come up with some representation, some physical representation of those processes that we can then integrate over the observed history. And it's primarily this parameterization that induces the uncertainty in the cooling effect of aerosol. So here I'm just breaking down the effective radiative forcing. This is the term that we refer to it as, this change in top of atmosphere radiation budget for the main anthropogenic forces. So CO2 is obviously the primary warming agent, and it has a forcing of around 2 watts per meter squared. This was as at 2015. It's a bit bigger than that now. The uncertainty is reasonably small on that. We have other contributions from methane and nitrogen dioxide and other halogens, CFCs, and ozone. Aerosol stands out both because it has this large cooling effect, but also has this large uncertainty. And when you tot up all the various contributions from the anthropogenic forcing, the large uncertainty from aerosol leads to a large uncertainty in this present-day forcing. Us climate scientists talk a lot about forcing, and we show lots of these kinds of plots. But as I spin up my group down at Scripps, I'm writing a lot of proposals, and I wanted to try and make this kind of link between uncertainty in the aerosol forcing to our ability to project future warming. I wanted to say something a bit more concrete about why we care about reducing this uncertainty. And so I had a paper recently with a colleague of mine, Chris Smith, where we looked at a kind of hypothetical situation of reducing this uncertainty and what it would mean for our ability to predict future warming. So we took one particular scenario for the future. So this is SSP 126 for those of you who know the lingo, but it's a Paris-compatible scenario that broadly keeps us below 2 degrees of warming at the end of the century. And the range of predictions here comes from an ensemble of simulations prepared for the AR6 report that span all of the uncertainty in the physical climate system, so cloud feedbacks, aerosol forcing, and so on. And the historical temperature is here in white. And so this agrees quite well with the historical temperature because this has been calibrated on historical temperature and ocean heat uptake and other things. But we nevertheless have this large uncertainty into the future. And in this ensemble, the aerosol forcing uncertainty is around 1/3 of a watt per meter squared. The central estimate is around -1.1. So we asked the question, what would happen if we do all this great science that we're hoping to do in the lab and we reduce that uncertainty? What would it mean for our ability to project future warming? And it turns out it depends. It depends on what the true value of the aerosol forcing is. So if we reduce the aerosol uncertainty from 1/3 of a watt per meter squared to 0.1 watts per meter squared, right? We improve it by a factor of 3. If we find that the aerosol forcing is on the small end of our expectation, so all these little complicated aerosol effects that I described actually have a fairly modest effect on the climate, and it comes in about 0.5 watt per meter squared, then this scenario keeps us below 1.5 degrees of warming at the end of the century at 95% confidence, which is good news. If, on the other hand, we find that by reducing this uncertainty, we narrow down what we think the forcing is, and we find it's on a high end of our expectations. It's a large cooling that we've been inducing over the recent history. That will lead to a large unmasking into the future as we reduce aerosol emissions. And this same scenario, with all the same socioeconomic choices that we make over the intervening years, could lead to more than 2 degrees of warming at 50% confidence. Right? And so that difference of 0.5 degree was dug into in quite some detail in an IPCC special report. They had a 1.5 degree special report that was commissioned. And there's a lot of detail about what that means for economies and ecologies and life on Earth. Some headline figures were the fact that 0.5 degree difference translates as something like $10 trillion in avoided damages at 2050, not even at the end of the century. Let alone 440 million people experiencing extreme heat that they wouldn't otherwise. And so, if we want to be able, as climate scientists, to provide policymakers and society with the best tools to decide how urgently we need to turn around these emissions curves, these kind of uncertainties are really crucial, and this kind of motivates a lot of the work that we do in the lab. So I'm going to use these I'm going to use actually this representation of uncertainty in future warming, to frame the rest of the talk in these three examples that I'm going to give. It was originally published in a paper Ed Hawkins and Chris Sutton wrote back in 2009. I recently updated this with CMIP6 data, but the story is pretty much the same. So if you take the fractional uncertainty in global mean temperature from across the CMIP ensemble, the contribution to our ability to predict future warming that comes from intermodal spread, and this primarily captures uncertainty in a physical climate, like forcing and feedbacks, that peaks at around 2050. If you look at the end of the century, the biggest uncertainty is what we decide to do as humanity, whether we decide to burn all the coal we find or take a more sustainable route. There's also a contribution from internal variability, so this isn't really weather on this timescale, this is more ocean variability and so on and so on. But this is kind of, so these two are irreducible, right? These aren't things that we can hope to constrain with better science or better models, but we would nevertheless like to be able to explore them, right? We'd like to know, we'd like to have a model for this invariability so we can say, so we can make statements with well-calibrated uncertainties, and we'd like to explore this scenario space so that policymakers can understand the implications of their decisions. To start with, I want to focus, though, on trying to reduce and improve this model uncertainty. And so the way we go about doing that, or the way at least I'm going to talk about doing that in this talk, is improving or using climate model emulation for improved calibration. And when I talk about emulation in this context, I really like this representation from Tom Buechler. He had this in one of his recent chapter, I think it was, on model emulation. And he defines kind of three different axes. So you have an interpretability axis, you have a representation axis, so like how representative can these functions be that you draw with your emulator, and how much physical structure do you embed in those representations. And so you can have a very interpretable linear regression model that doesn't give you a lot of representation power almost by definition. Maybe a random forest is a bit better. Or you can go whole hog and just train a really big, deep CNN or neural network, which makes it difficult to interpret. I appreciate there are ways to do that, but it's not as interpretable as linear regression. We might hope to encode more physical structure by imposing a physical loss or other approaches that might impose more physicality on these structures. But what I want to talk is what I kind of maybe somewhat biasedly think of as a sweet spot, which is using Gaussian process emulation. So Gaussian process regression is, I would argue, more interpretable than a CNN, maybe not as expressive, but more interpretable, to do parameter estimation. And so here we're retaining the full physicality of the climate model. We're retaining the physical structure, and we're using this emulation to better calibrate and better tune those parameters. So what does that look like? I'm going to get pretty abstract for a moment, so bear with me. If we think of a climate model as some complex function f, right? It takes some inputs, x, which are emissions of CO2 and greenhouse gases, and a whole load of parameters, and often these are just left, right? So there's some comment in the Fortran code that says this parameter works for this parameterization, and maybe there's a link to a paper, maybe there's not, but there's a bunch of these in the model, and you run the climate model and it produces a whole load of output y. And what we'd like to be able to do is, given a subset of those outputs that we have observations of, which I'll call yo, we'd like to know the inverse, right? We'd like to know what observations, if we run the inverse model, which parameters we would get if we ran the observations through our inverse model. We don't have an inverse model, and even if we did, this probably wouldn't be well framed. We can think about it probabilistically. We can turn it into a statistics question and ask what the probability of a set of parameters is given our observations, and I can write down Bayes' theorem and feel very clever, except the difficulty is that we don't know this likelihood, right? We don't have this likelihood term. So we turn to a set of tools called likelihood-free inference, and there's a rich literature about this. But the tool I'm going to use is pretty much the simplest way you can go about this. It's referred to as approximate Bayesian computation, or sometimes just rejection sampling. And I'm going to walk through the 3 steps right now. It's super straightforward. So the first thing you do is draw a set of parameters from your prior. So this is a Bayesian approach, so you have to have a prior. even if it's a non-informative uniform prior. You run that forward through your model. So you put those parameters in your model and you run the model and it produces some output. And the thing is, you accept those parameters if some distance between the observations and the output is less than some tolerance. So if your observations are close enough to, sorry, other way around, if your model output is close enough to your observations, then you keep that set of parameters. And if they're not, you don't. So you can see that as epsilon goes very big, then we accept everything and we end up just getting the prior back. That's kind of obvious. What's less obvious is that as epsilon tends to 0, you can show mathematically that you're generating observations directly from this posterior. You're sampling from this posterior. And there's some nuance and some tricks in there. The biggest of which is the fact that you need many, many samples, right? We have to run this hundreds of thousands of times to densely sample our posterior. Particularly because as you make epsilon smaller, you're rejecting more and more of these samples, right? And so it becomes fairly inefficient, or it can become inefficient. And so that's where the emulation comes in. We have a surrogate model or an emulator to approximate our forward climate model. So approximate this f as a function of theta. And I'll come back to that in a moment. The next thing I want to just touch on briefly is this rho, this distance metric. There's various different ways of framing it. You could use MSE or something else. In reality or in practice, we use something that is sometimes referred to as an implausibility metric, but it's really just the standardized Cartesian distance between the emulated predicted output given our theta to the observation. So this is just the absolute distance between these two things, divided by the sum of the variances. So we have some uncertainties that we'd like to account for. First of which is the fact that we have an emulator uncertainty. The fact that the emulator we use is not a perfect representation of the climate model. Second is that we have some uncertainty in the observations themselves. These are not perfect. They're not necessarily the truth. And we have some structural uncertainty. We have the fact that no matter how we twiddle the parameters, we might not exactly reproduce what we observe because we're trying to represent an average process over 50 kilometers, or because our functional form of our microphysics scheme is not perfect. But given that now, this implausibility, if you like, is just how many standard deviations away is this model configuration from the observations? And what we do is we say, well, if it's more than 3, if we're more than 3 standard deviations away, then there's this rule of thumb that holds that for any unimodal distribution, if you're 3 sigma away, that correlates to at least 95% confidence. So then we rule out any parameter combinations where the model is more than 3 standard deviations away from the observations. So rather than kind of doing an MCMC, trying to find the very best individual set of parameters, we're kind of doing a rule one out. This is close to history matching, that kind of idea, where you rule out parameter combinations that are just incompatible with the observations. And you see where that takes you. Okay, so I mentioned emulation. So I'm gonna walk through a kind of more concrete example. That was all fairly abstract. So I'm gonna go through a concrete example here where we have 3 parameters that we're looking to vary. One is the black carbon number. So this is just a scaling on the amount of black carbon, a particular aerosol species in our model. The other parameter is the imaginary part of the refractive index at 550 nanometers. So this is the absorptivity of the black carbon at that particular wavelength, so we can scale that up and down. And there's another parameter which I can't represent on this screen, which is the removal of black carbon. So there's some process that removes black carbon, so wet removal primarily, that is somewhat uncertain, and we scale that. And the Y that we'd like to compare with observations is the absorption aerosol optical depth. It's how much absorption is there through the atmosphere due to aerosol. And we sample that space. So each of these white dots is a 1-year climate model simulation. Sampling this space using Latin hypercube sampling. It's kind of just random sampling, except trying to keep the points away from each other. If you just do purely random, you end up with some points clumped together, and it's not optimal for filling the space. So there's some way of getting around that so that we fill the space. And that's our training data, right? In machine learning parlance, this is our training data. And this just becomes a regression problem. So we have our simulations, we hold some back for testing, and then we fit a regression model through that. And it, you could use a linear regression. In this case, it's a pretty nonlinear process. We use a Gaussian process regression because it gives us well-calibrated uncertainties, deals with the nonlinearities, and deals with a relatively modest amount of data. But now with this emulator, I can ask for any given combination of parameters, right? I could ask BC times 0.6 for an IRI of 0.2, what's the AOD that the model would spit out? And I get a pretty decent estimate of what the model would do for that parameter combination. And so now I can stick this inside my ABC loop and do sampling. I can just pick hundreds of thousands or millions of samples from the prior distribution and say, does this AOD match what I measure from the observations? If it doesn't, it gets a red dot and I throw it away, and if it does, it gets a green dot and I keep it. And if I do that, I start to build up, I start to sample this posterior and I get some interesting things pop out. So we started from uniform priors here. So what's interesting to note is that these marginal distributions haven't really changed. They're still pretty flat. We haven't squeezed those at all. But we've started to find a slice through this space that is compatible with the observations. And this kind of makes sense if you think about it. So there's different ways that you could get the same amount of absorption in the atmosphere. You could have not a lot of very absorbing aerosol, or you could have quite a lot not very absorbing aerosol, right? And those two quantities would give you about the same amount of absorption. And so Ken Carr's law would call this equifinality. It's a kind of fairly common issue when you have various different parameters and only so many observations. But this is a good start, because now I can say, okay, well, now I go and measure the actual amount of black carbon in the atmosphere. I can take aircraft measurements or in situ measurements and get a constraint going this way, and then I've really started to slice down this posterior, and I start to know, where the good parameters lie, or the plausible parameters lie in this space. And so we built a machinery to try and make this easier. We've got so building on the community into comparison suite, which is actually where I started in this field, to co-locate the models and the observations. This is your first task if you're going to compare models and observations. And then that plugs into this Earth system emulator that is really a thin layer on top of kind of Python machine learning libraries such as scikit-learn and GPFlow and others, but hooks in nicely to X-Array and Iris and other libraries that we're familiar with in the field, and also provides this inference and calibration engine. And that ABC engine that we wrote, this rejection sampling, is written in TensorFlow such that you do this rejection sampling on the GPU. So you have this regression model that has some weights on your GPU, and you can just put the observations there and just keep chugging away. The GPU just keeps drawing samples from your prior and then throwing away those at a rate of something like, so we can do this, we can generate whole maps of climate model output at like 100,000 samples a second or something on a GPU, on a modest GPU. So you can very quickly get good statistics. And it extends to more parameters, higher dimensional parameter space. I don't expect you to read this. This is just an example of one of the ensembles we worked with in the UK climate model, where we looked at 30 different parameters, looking at the aerosol processes in the model, and using this machinery then to start to squeeze those uncertainties. And by doing that, you then start to chip away at the thing you care about, this aerosol forcing uncertainty. So on the left-hand side, just an example of a plot from a paper that we had back in 2020, where we used this technique to reduce the uncertainty in the aerosol direct radiative forcing in this model by comparing with observations of AOD and other things. And on the right-hand side is another paper, so this is from Isabel McCoy and others, where we looked at constraining the IRF ACI, so this cloud brightening effect, using exactly the same thing. She used observations of cloud droplet number, and again, we were able to squeeze that uncertainty in this model. So there's still work to do. There's some great work going on with CAM6. So this is a paper from CISL just up the road in Wyoming with Dan McCoy, who's been working on constraining this PPE using observations of liquid water path and so on. So this was developed here at NCAR when Andrew was still here, and Trudy and others are working on it. So that is ongoing. And there's some interesting work from the UK model, from Leighton, looking at the trade-off with the amount of observations. So those of you who are kind of mathematically inclined might recognize that this distance metric that I described will suffer when you have many, many observations. If you have lots of observations, you get this curse of dimensionality. And no matter how many parameters you try, you might not get a very good constraint. So we kind of explored that a bit in this paper. But I think there are opportunities to use machine learning to kind of cheat this curse of dimensionality. We can find some latent representation that gives us better constraints. So I won't go into too much detail on that, but these are kind of the directions we're heading with that. Okay, I also wanted to talk about scenario exploration. So this is this second kind of type of uncertainty, if you like, and how we're using Climate Bench, which is what came out to do that. So just briefly, some of you will be familiar with this. Apologies if you all are, but there is a component of the CMIP exercise which are focused on producing different scenarios into the future, and this is called Scenario MIP, and they produced a set of socioeconomic pathways, they're referred to as, that represent some kind of plausible sampling of the future of humanity, right? No less grand a task, that somehow span different climate outcomes. So we have a sustainability-driven pathway that leads to a relatively modest future warming. We have a fossil fuel development-driven policy or pathway where we basically just burn everything we can find underground, and that leads to a very large degree of warming in the future. And there's a couple of kind of intermediate scenarios here in between. But, you know, I don't need to tell you that that's a very sparse sampling of all the different ways that humanity might get to 2100. And in the policy world, or at least in the adaptation mitigation world, they don't use these scenarios. These scenarios are used to train emulators that they then use to explore this space. So given these pathways of emissions of CO2 and methane, which correspond to those scenarios I just described, as well as short-lived forces such as sulfate and black carbon, they will emulate the model response to these forcings to produce the global mean temperature for a given climate model or a set of climate models. And these may be more physical or more statistical, and there's a whole class of models that do this. But these form the basis of the link between IPCC working groups 1 and 2 and 3, right? These kind of models that just take global mean temperature. They chuck away the climate models, and I hate to break it to people who work daily on these things, but they're just not used, right? If you want to go regional, then what they do is take that global mean temperature and do pattern scaling, right? And that could be a linear pattern scaling, or it might be something a bit fancier. So there's this Mesmer model that now uses neural networks to do that. But either way, you're washing away any regional effects of these forces. So black carbon in particular is, in the present day, most strongly emitted in South and East Asia. And we expect the climate effects of that agent to be primarily felt in South and East Asia. And it doesn't have a huge impact on global mean temperature. So in this framework, it just doesn't end up mattering. And any policy work that looks at the effect of BC based on these models will be biased and incorrect. But when you frame it like this, as an emulation, as a regression problem, then you can start to think, well, maybe we can unlock the tools of machine learning to do this in a different way. So actually what we did in this Climate Bench benchmark was to take maps of the emissions of sulfate and BC and just regress those onto maps of climate model output directly. So this is a map of global mean temperature at the end of the century under SSP 245. And this is precipitation, because once you're doing machine learning, it doesn't really matter what you emulate, right? You can pretty much emulate whatever you like, or you can do the regression and see if it holds. So that's the framework. So we take we frame it as a machine learning problem, and then the question is, what training data do you have? So this is more of a kind of ensemble of opportunity, as opposed to the Latin hypercube sampling. We're just grabbing whatever we could from the CMIP archive. So we take the input from IPS, the input data that's actually used to drive the climate models, and we combine that with the outputs from a particular climate model. In this case, it's NORI SM2, because that's what I had available. We're doing this on CSM2 now as well. It doesn't really matter. And we just grabbed whatever scenarios and simulations we could find. So we take a selection of the future socioeconomic pathways, these green ones, that span a range of future likely future scenarios. Some idealized scenarios, so like abrupt 4 times CO2, 1% CO2, that kind of get you into the corners here of this space. We looked at the historical simulation plus some DA simulations, if you're familiar with those, where you just do historical greenhouse gases or just historical aerosol. And again, that starts to kind of try and get you into the corners of this space. And together it does a reasonably good job of kind of filling in this space of different emissions. It's not perfect, but it does a reasonably good job. And so we train on all of this data. We hold back one particular scenario, which was kind of middle of the road for testing and for testing, so we can evaluate the models. And so this is what comes out after you go through that exercise for a couple of the pretty simple baseline models that we put together for this benchmark. So on the top row, we have temperature at the end of the century. Sorry, I'm still getting used to this pointer. Temperature at the end of the century. Here we have diurnal temperature range at the end of the century. So this is daily max minus daily min. Two of those columns are machine learning emulators, and one of them is the full complexity climate model simulation that took weeks and weeks on a supercomputer to run, right? And the others were just produced on my laptop. It's this one on the right is the climate model. Maybe you guessed it, maybe you didn't, but I think you'd be pretty hard-pressed to tell the difference just by eyeballing them. They do a really good job of capturing both the North Atlantic warming hole here, they capture Arctic amplification, they get this weird patch over the Amazon that NORI SM2 seems to produce. Even in precipitation, so this is mean precipitation, and the top annual mean that is, and here we have the 90th percentile in precipitation. You see the shift in the ICCZ gets captured by these models, and this was what really surprised me, actually. I was really surprised how well these models could do at predicting these changes. If you look at difference plots, so we have difference plots in the paper, these models underestimate the magnitude of this change to some degree, but on the whole do a pretty good job. So then, as an atmospheric physicist, the question that, bugs me is, do we trust these things, and how do we check for energy conservation and physical constraints and all these other things that we worry about with our climate models? One test we could look at might be global energy conservation. So we've known for a couple of decades now, there's this nice paper from Miles Allen, that global mean precipitation change is energetically constrained through global mean temperature. It doesn't follow Clausius-Clapeyron. It follows something like a 2% per Kelvin relationship. And on the right-hand side is what happens with the NORI SM2 is the squares, the crosses, and the emulators are the circles. And so the GP does respect that limit, but it actually underestimates that sensitivity. The neural network does a better job, particularly at low temperature, but it's starting to underestimate at higher temperatures. So, it kind of respects energy conservation, doesn't necessarily reproduce the same sensitivity. If you're critical and skeptical, you might say, well, if it does a reasonable job of predicting temperature and it does a reasonable job of predicting precip, then you should expect it to get the relationship. So it doesn't necessarily tell you anything you didn't already know. But it then begs the question, how can we put some physics back into these things? So I want to briefly introduce something that I'm really excited about, where we use energy balance models, so the basis of these projections that I showed you before, as a kind of constraint on these kind of simulations and emulators. So these projections were produced by one particular energy balance model. This is an impulse response type model, where you model the change in heat in a given box in the atmosphere, so you model the Earth as 3 boxes, broadly representing the atmosphere, shallow ocean and deep ocean, and that's related through this ODE to the forcing and feedbacks. And this kind of energy balance model is the physics on which we trust these projections, right? These projections don't come from climate models. They come from these energy balance models because this is the physics we trust. It's fundamental thermodynamics, right? If you want to know what's going to happen in 100 years, you want to be using thermodynamics or something, pretty bulletproof. The Earth is an isolated body. You put more energy in, it gets warmer. These are nevertheless informed by climate models, right? We still need to know the forcing that goes in. We need to know the feedbacks. They're also calibrated against measurements of deep ocean heat uptake and other things. But I wanted to try and use this physics, this thermodynamics in these emulators. And so one of my PhD students in Oxford, Shaheen, created this fair GP, which I want to describe here. So the idea is we take one of these impulse response models, and in that model, there's some assumed form for the forcing of each agent. So you have a concentration of some gas, like greenhouse gas or aerosol concentration, and the forcing is a fit to some logarithmic term, a linear term, and a square root term, right? And these f's are just coefficients that are learned for each climate model. It's a bit empirical. It fits, it does a reasonably good job, but we don't have any physics for this bit. So what we said was, well, let's take that as kind of a starting point, right? This will be the mean function of a Gaussian process that models that forcing. So the GP gives us more flexibility, but falls back on this kind of, physical empirical relationship. This retains the original formulation when there's no data present. So as a Gaussian process, right, the mean function is what it goes back to when you don't have any data. And then it has this Bayesian robust approach for adjusting that when it has new data from simulations. But importantly, the solution to this ODE is now also a Gaussian process. So if this F is a Gaussian process, then the solution to this ODE is a Gaussian process that automatically satisfies that ODE. So we might also want to think about internal variability and how we account for that. Some of you might be aware of Hasselmann's seminal papers in the 70s and 80s, whereby we model the internal variability in the Earth system by introducing a white noise term in these kind of models, just to model the forcing. When you put this white noise term in the forcing, it ends up as red noise in the response. We don't need to go into those details. But by simply adding a noise term to this deterministic Gaussian process forcing that we had before, it turns out that the large T solution to this equation is identically a Gaussian process with a Matern covariance kernel. So we can kind of embed this into our GP, and the solution is still a GP. So that allows us, kind of in simple terms, to quantify both the model uncertainty and the internal variability in our model, both in combination and independently. So what does that look like? I'll just do it in one dimension because it's simpler. This is for SSP 245. The blue line is the true NORI SM2 global mean temperature response. The red dashed line is the prior, is the physical model, the fair energy balance model. It does a pretty good job of capturing that response in this scenario. But once we train our GP, sorry, I'm going to go back a second, and our Gaussian process is the orange line, right? So before it sees any data, it's just following fair GP. It's just doing the same thing. It has some wide uncertainties because that's just what it started with. If we show our GP some data from some other simulations that we haven't, that we're not showing here, our posterior model fits this data almost perfectly, right? It really just nails it. We have some uncertainty estimate, some well-calibrated uncertainty estimate that grows into the future as it becomes slightly less sure about what the true response should be. But if you notice, our internal variability estimate, this slightly lighter shading, stays pretty much constant throughout, which is kind of what you'd expect. The noise model should be roughly constant. As the model gets out into the future and it's starting to get away from its training data, notice that the uncertainty becomes larger and the model reverts to the physical prior, right? It's going back to where it should be when it doesn't have any data. We can extend this spatially, so we can take that kind of pattern scaling approach. It provides a pretty simple model, so we just have local coefficients for the global mean temperature plus some constants. And it might not surprise you by now, but so yeah, this is just what I said. But if we substitute this guy for our Gaussian process model that we just built, it turns out that this thing is now also a Gaussian process because it's all just linear. So we can write our map of temperature as a Gaussian process with this covariance, and it's still a GP. And the nice thing about that is we can now update with local temperature observations and get a posterior which encodes any observed deviation from that linear scaling. So we have a prior mean, which is just our linear pattern scaling, right? And our Gaussian process learnt posterior correction, which accounts for nonlinearities, which particularly show up here, interestingly, around Greenland, where ice is presumably playing a role, and glacier melting and so on. And we also get well-calibrated uncertainties. We have an upper bound, a mean, and a lower bound, and this is the true value, which lies pretty nicely in the middle. Okay, so I'm pretty excited about ways to do that, to encode these physical priors into our knowledge. The other thing I want to very briefly talk about is, how we might model this variability. So at the moment with this model, we don't have a, spatial map of the covariance. So the one thing missing from this thing at the moment is we don't have a spatial covariance, because that gets quite expensive with a GP. There are ways around it. But another way of coming at this is modeling that spatiotemporal noise, what we might call weather, using diffusion models. And there's a couple of papers coming out at the moment which I think hint at how we might do that. There's this diffusion model, diff with a Y, that was just submitted to ICML, which has some exciting opportunities. So this one is applied at the moment to the weather problem, where you do forecasting based on updating noise. But I think we can use similar things for the climate process as well. I won't go into the details of that now. But I also just want to talk about how we might bring together that initial thing on calibration that I talked about and this final task on modeling the climate. So I'll go back to this slide a second. One thing that is slightly galling as a process-based modeler, I guess, if you had to pin me down you put me in a box, is the fact that the aerosol forcing, so the uncertainty that I described right at the start, the best constraint we have on that currently is the fact that we didn't see any warming in the 60s, any cooling in the 60s and 70s. So the aerosol forcing was at its largest compared to CO2 in the 60s and 70s, and we didn't see any statistically significant cooling. And so that puts a pretty hard limit on what the aerosol forcing could be. And so I think there are opportunities then to use this kind of fair model trained with these kind of ensembles that explore the parametric uncertainty, build an uncertainty model for that, and use the temperature constraints from that to constrain our PPEs. And while we're at it, we could use maps of temperature to get more information. And so I talked about this at AGU. I can go into some details here if you like, but kind of trying to bring in this top-down constraint, use a temperature constraint as well for our microphysical processes. So I'll briefly wrap up. Hopefully I've convinced you there are some ways or interesting ways that machine learning can be harnessed to accelerate climate science, and that we're using these techniques to build Earth system emulators for parameter estimation and constraining uncertainty, and indeed using similar emulators for exploring scenario uncertainty with high fidelity outputs and robust uncertainties. And we have physical constraints on the global response, and we've demonstrated ways to directly encode those in physically informed Gaussian processes. There will be multi-model emulators, which we just submitted a paper on, which will help us explore and quantify kind of structural models differences as well between models. So I'll leave it there and happily take any questions.
Any questions from the audience? Any questions from the audience? Dama.
Yeah, great talk, thanks. Are there any efforts in like the CS methods community to do more physically informed GPs?
It's a good question. Not that I'm aware of. GPs are a little bit niche. So actually coming from the UK, people use them a lot. There's a lot of people working on GPs in the UK. I don't know why. I think it's just a historical thing. It's not a big community, but I think they seem to lend themselves quite naturally to that kind of constraint. And I think there are opportunities to do it more, but maybe you know better than I do. I don't know.
Yeah, I saw a few papers last year at ICML, but
okay.
I don't know about other conferences.
It'd be great if you could share them. That'd be cool.
There's one question online.
Hi, this question is from Marcus. For the rejection sampling, have you tried accepting/rejecting based on the probability defined by likelihood/prior rather than fixed threshold for that likelihood/prior?
Oh, interesting. Okay, yeah. So let me find the right slide. So if I understand Marcus's point correctly, the idea is, or his suggestion is, that we could make epsilon variable. I find it a little bit harder to interpret if you do that. So the group in leads treat epsilon as a parameter in order to generate, so they fix n, they fix the number of samples that they will draw. They pick 1 million, which is somewhat arbitrary, but it's a big number. You pick 1 million, and then you fiddle with epsilon so that you have enough samples in your posterior. But that feels a little bit suboptimal because, really you want to make epsilon small ideally, but you want to make your posterior small, but you don't want to rule out parts of parameter space prematurely. It kind of all becomes a little bit philosophical, and I think there's some benefit in the community to being more transparent about how we make these choices and also about what our priors are. There's a lot of literature, and I tried to thread this together a little bit in the paper, but there's a lot of differences, very subtle differences between history matching, parameter tuning and calibration, and this kind of history matching and MCMC that Tapio is doing. They're all kind of related, but they have slightly different objectives and slightly different, therefore, I don't want to say biases, but they'll give you a slightly different answer. And so I think we should be clear about how we do that and what those biases are. And I think if it's the marker, so I think it is, then we should definitely do some sort of benchmark where we compare all these things and we see how those compare.
One kind of follow up to Marcus's question, unless there's other ones online. I guess could you, if you say assumed a kernel for if you have instead of like a fixed E, you had some kind of kernel where you where your chance of rejecting it would go up at the further, as you asymptote toward wherever your epsilon is. Does that still give you transparency, but maybe does that make a better balance between a fixed epsilon and something that's completely random, or does that introduce its own biases potentially?
So you say that if you have, so you get a different implausibility. You get, so you're more likely to reject an implausibility of 4 than you would be of 2. Is that what you mean?
Yeah.
I think it all ends up the same. Okay. I don't. With enough samples, it feels like you end up in the same place, but maybe I'm wrong. I appreciate this hard cutoff. It seems somewhat arbitrary.
But then you can vary and see how arbitrary it is, and
you can, yeah, exactly, you can. The other thing about this is, one thing that you get from this is you can just look at these implausibilities themselves, right? You can look at in observational space and say what observations are providing the strongest constraint, and you say, well, this observation is. So what we found in this simple 3-parameter example was when we brought in aircraft data of black carbon, we found that there were some observations that were like 6 sigma away from this ensemble. And we're like, well, you just couldn't match it at all. And that indicates a structural bias, right? And we dug into it, and it turns out the model was just putting the biomass burning plume 3 levels too high or too low. I forget which way around. And so no matter how much you turn up the emissions or turn down the emissions, it's just never going to get the right amount of BC in that location. So you can, in that case, you can either inflate your kind of structural uncertainty variance, or you can be a bit clever about how you aggregate your observations and say, rather than getting exactly the right black carbon concentration in that grid cell, you say, what's the burden, right? How much black carbon is there in that column? And then it doesn't exactly matter where you put the vertical. You go back and you fix that in your model separately, and then you tune the emissions this way. But it's a way to somehow improve the way we calibrate these complex models.
Oh, we have another question from online. Could you comment on usage of explainable AI and interpretable AI in your machine learning work? This is from Jyothram Vivekanandan, and I apologize.
Yeah, no, that's a good question. So I get a little bit philosophical with this in the climate bench paper, because I kind of think interpretability is in the eye of the beholder, right? So some models may seem more interpretable to some people than others. Wait, I have this. Oh, it's back here. 1 second. So I have this axis of interpretability that, you know, after Tom's stuff, and I think, you know, linear regression is probably, you know, simpler than random forest, is probably simpler than CNNs. But what about Gaussian processes, right? I kind of indicate roughly here that I think they're somewhat interpretable. I think but you have to understand how Gaussian processes work. They can be seem kind of complicated because they're quite mathsy, right? But once you have read a little bit about it, they're not so complicated, and you pick the kernel, and the kernel tells you roughly how smooth the functions are that you're drawing from, and actually I think they're fairly interpretable. So I wouldn't like to get too much into that. The Gaussian processes do allow you to inspect, you know, the weights that they've learned, and you can inspect. The nice thing about these is they give you well-calibrated uncertainties. So you know, you can look at the attention of a network or look at the weights, but it's very hard to get well-calibrated uncertainties from a neural network. So I think in that kind of arena of XAI interpretability, I think Gaussian processes have a big advantage. I think generally you want the simplest model that you can use to explain the thing you're trying to do, right? And for the climate bench stuff, it turns out linear regression works annoyingly well, right? So reviewer 2 was like, oh, hey, you should do a linear bench line. I was like, right, fine, I'll do a linear bench line. And it like beat the CNN on some of the things. And you're like, well, okay, well, it's good to know, actually, right? It's good to know that you can just do this linearly. And the pattern scaling, in that sense, is not terrible. It's a slightly waffly answer. I hope it.
Hey, thanks. I also have a question on the sampling process, but I'm going to skip that one for now.
Okay.
When you talk about the emulating different scenarios, you mentioned that you held out a sort of run-of-the-mill observation, like scenario.
Yes.
And decided how well that would do. I'm curious to know, did you test if instead you held out one of the more extreme examples? Like, this is the obvious question, right? How would that perform? How does that perform?
That's a really good question. Let me see if I have a plot. No, I didn't put that one in. We didn't do that in this climate bench. So, you know, I would expect the linear model to do okay. The GP, it depends on your mean function. If you build your GP such that the mean function is 0, it'll revert back to 0 and it won't look very good. The neural network will do who knows what, right? Bets are off. But it's a good question. It's a good test, right? How well do they extrapolate? The random forest will just sit at whatever the maximum. It won't extrapolate at all. So it kind of depends what you want it to do, I guess. You know, will bias how well you think each one is doing. What should it do if you've never seen that scenario before, right? Again, I would argue that the Gaussian process does the right thing. It just gives you a very large variance. It says, this looks like nothing I've seen before. Take it with a pinch of salt. The physically informed GP, we actually did do this test. So that paper is just about to come out in James, and we did this extrapolation test. And because it has this physical prior, it can fall back on. It does very well. I think people worry a lot about generalizability for neural network or for machine learning in general in the climate setting. In this case, I'm not too worried because you can just train it on 4 times CO2, right? And it will, or you just give it a really big scenario that you hope you're never going to see in real life, and then you're kind of safe. So I don't think it's too much of a problem. Where I do worry, though, actually, is in this case, although we've looked at different magnitudes of aerosol emissions, almost all of the scenarios have the emissions coming from North America, China, India, and Europe, and North America, and some shipping, right? If I take one of these emulators and I ask what would happen if I put all of the sulfate emissions in the South Pacific, wouldn't have a clue, right? It wouldn't know. And so there's some inherent kind of dimensionality in here that it would be interesting to explore and understand. Particularly if I want to give this tool to policymakers, right? I want to be able to communicate the limits of the training distribution and where you should trust this thing and where you shouldn't.
That makes sense. So, and with the other one, the sort of argument we're making here is we can sort of capture these extremes sort of beforehand.
Right.
Oh, yeah, sorry.
Yeah, so you just want to make sure you're interpolating rather than extrapolating. Yeah. And we can do that when you design the training data. But I think this is, so what's interesting is, CMIP 7 is coming up, and there is real debate about what these scenarios should look like, right? Should we have a really high scenario? Is that just a waste of compute for everyone to be running 585? In what is a hopefully increasingly implausible scenario? Or should we spend more effort on these kind of slightly lower, more likely scenarios? I might suggest that actually, given what these models are actually used for, you'd be better off just getting in the corners, right? Just do a Latin hypercube sampling almost of the emission space, right? And that might be a more efficient way of building these emulators.
We're at 2 o'clock. Duncan will be, I guess, around a little bit the rest of the day. Yeah, reach out to me if you want to reach out to him with more questions. We're also having, if you want to come up to the penthouse, we'll have a more extended Q&A. So with that, thank Duncan one more time, and really appreciate it.
Thank you.